In this module, we will discuss propagation of electromagnetic waves inside perfectly homogeneous linear isotropic dielectric materials. An example of a linear isotropic homogeneous dielectric material is vacuum or free space. What is this electromagnetic wave and why should we be interested in studying its propagation, and how can Maxwell's equation help us tell how the wave would propagate? Can Maxwell's equation actually say that okay, this particular process is responsible for generation of the waves and then also describe its propagation? The answer to both questions is yes. Maxwell's equations, if you solve them under appropriate conditions, you can actually show that under the existence of some time varying currents, right, and which results in accelerated charges, there will be electromagnetic waves generated. This was predicted by Maxwell's equations and later experimentally first time verified by Hertz. Okay. Sometimes that these waves are also called as Hertzian waves, just to honor the fact that Hertz was the first one who generated electromagnetic waves. Now, we have already seen Faraday's law and modified Ampere's law, right? In Faraday's law, we have curl of electric field equal to whatever the time variation of the magnetic field at a particular point. So, you had this small region of space and then the curl of electric field, which could be obtained by putting up an imaginary conducting path, a loop of conductor. The source of that EMF was actually the time variation of magnetic field, right? So, how is magnetic field generated? It is generated by time varying current. If the current is not time varying, then it's still possible to generate magnetic fields, but in that case the magnetic field will be static with respect to time. So, if the magnetic field is static with respect to time, then there will be no curl of electric field. In any given region of space, there won't be any curl of electric field. Remember, Faraday's law is actually matching two things. One, on the left hand side is the space variation of the electric field in the form of the curl, and then the time variation of the magnetic field, right? So, if the magnetic field is not varying with time because the current was steady and hence the magnetic field was also static, there won't be any space variation of electric field. Electric field continues to be completely delinked with magnetic field. Okay. So, the first rule is that if you want to produce electromagnetic waves, you want to have time varying magnetic field. At least that's what Faraday's law tells us. Only when you have time varying magnetic field, you will have curl of electric field, a space varying electric field, right? So, a time varying magnetic field is generated by time varying current, that is di by dt must be non-zero. If di by dt must be non-zero, that means that d square q by dt square must be non-zero. Why? Because I is dq by dt, current is rate of charge. So, only when charges are accelerated, there will be time varying magnetic field which will generate a space varying electric field. Now, if you look at the space varying electric field and then if that space varying electric field is also varying with respect to time, right, because the charges are actually accelerating, changing with respect to time. So, the corresponding electric field would also be varying with time. So, this time varying electric field or time varying electric flux vector D vector would in turn generate a space varying H, correct? This is in the form of displacement current. A displacement current which is varying with respect to time will generate a space varying magnetic field, right? So, this action actually couples together. You have time varying magnetic field in a region generating space varying electric field. The time varying electric field or D field, but in case where we are assuming D is proportional to E, time varying electric field will generate a space varying magnetic field, and then this would actually couple together and correspondingly you would actually have propagation. But remember, what is the source of all this? The source of all this is still the charges or equivalently the currents, right? The time varying current is responsible for generating time varying magnetic field. Time varying current automatically implies that you are dealing with time acceleration of charges. Okay, now this was a very qualitative picture of how waves are generated, and the further propagation is actually sustained by the two self-consistent equations, that is Faraday's law and modified Maxwell's Ampere law, or modified Ampere's law, or Maxwell Ampere law. So how do we capture all this in terms of a certain equation or a set of equations that would help us understand this propagation of waves? Furthermore, what is the characteristic of these waves, right? So are these waves exhibiting some sort of a known time dependence? Do they exhibit a particular spatial mode? Like for example, you might have seen, right, you drop a pebble in the water tank, then the waves would actually all, the surfaces would all go nicely as a spherical surfaces, right? So all these rings or spherical surfaces. Would we actually get only those kind of waves, or is there any other kind of waves that are possible? We will see all these answers when we develop the wave equation. Okay, so the goal here would be to develop wave equation. Okay, to do that, let's begin by writing Faraday's law. Okay, so we know what is Faraday's law. Curl of electric field is equal to minus del B by del T, right? Since we will be considering mostly non-magnetic materials, we have B equals mu 0 into H, right? That's the simple relationship between magnetic flux density B and magnetic field H. Okay, so we'll have this equation. Therefore, substituting for B equals mu 0 H in this Faraday's law, you get minus mu 0 del H by del T, which is curl of electric field. What is the nature of electric field and magnetic field? What functions are these? So electric field in general will be a vector, but it should also be varying with time, right? So we typically denote this part of being a vector as well as varying with time by saying that electric field is a function of both the space variables. This R, if you remember, is the position vector, that is the field point that we were considering. So at any point, R itself is a position vector, and the result of this position vector is also a vector. So electric field is actually a time dependent vector field. Okay, so this is typically how we denote. If the electric field has to point only along a particular direction and be independent of time, then we will have appropriate substituted expressions for that one. Okay, but for general case, electric field will be function of both space variables as well as time variable. Okay, similarly for magnetic field H as well. H will also be function of R and T. Alright, so this was Faraday's law. What about Maxwell Ampere law? Maxwell Ampere law is curl H is equal to J plus del D by del T. Okay, we will assume linear, isotropic, homogeneous media for which D will be epsilon 0 epsilon R into E. Now instead of writing epsilon 0 into epsilon R, I sometimes shorten this and simply write this as epsilon E. Okay, again remember D is D of RT and E is E of RT. Epsilon is a constant, it includes the free space permittivity epsilon 0. If the medium that we are considering happens to be a dielectric with epsilon R greater than 1, then it would be epsilon 0 into epsilon R. What about J here? J is actually the current that we have. Okay, so if you'll have to wait for antennas to really understand how waves are generated, but with an antenna what happens is that you take a particular conductor, okay, and then connect a time varying function generator, function generator which will change the voltage here, and then this is an antenna, a typical antenna, and there will be currents which are induced in this antenna, and these time varying currents are responsible for generation of electric and magnetic fields. Okay, so this is the way that are generated, and the J, the current density vector J, is actually referring to this particular current. Okay, it is actually what is sometimes called as the source current. Okay, it is the current at the antenna surface. Okay, but what we will be assuming is that we are very far away from this region. Okay, no doubt currents are there. Currents are the reason why we have magnetic and electric fields and hence the electromagnetic waves, but we will be considering the electromagnetic field behavior or electromagnetic wave behavior at a very far away distance. Because of that, I can safely turn off J. Okay, only because we consider region far away from source currents and any charges that we have. So in the region we are considering, there are no free charges, there are no free currents. Okay, this implies that we have J is equal to 0, and for future reference rho v is also equal to 0. Okay, so these two equations are sufficient for us to show that electromagnetic waves are generated, and to do that one, let us write down these equations once again, and then let me show you how waves are generated. So I have curl of electric field equals minus mu 0 del H by del T. Curl of H is equal to epsilon del E by del T. Okay, if it is free space that we are considering, let's consider free space for now. Epsilon becomes simply epsilon 0. Okay, in case epsilon is not epsilon 0, then you will have to replace epsilon 0 by epsilon 0 into epsilon r. No big deal. Okay, so you can see here that on one side I have space variation of a vector field. In this it is the electric field which is varying with space, and here it is the time variation of a vector field which is magnetic field H, right. Similarly, you have space variation of the magnetic field linking to time variation of the electric field. Okay. Now I can write down a wave equation in electric field E or magnetic field H. Okay, customary to choose electric field E. Okay, we have some sort of an understanding with electric field E, so we choose electric field E to write down the wave equation. You can follow a similar process to write down the wave equation for magnetic field. Okay, so how do we write down the wave equation? Well, I take the curl of this first equation. So let's call this as 1. Okay, call this as 2. 1 corresponds to Faraday's law. So I have curl of electric field, okay, is equal to curl of minus mu 0 del H by del T. Now I can take curl inside this bracket and interchange del by del T and curl operations. So I get minus mu 0 del by del T curl of H. But I know what is curl of H from equation 2. I know what that is. So that is equal to minus mu 0 del by del T of epsilon 0. Epsilon 0 being a constant can be pulled out. So epsilon 0 comes out. And then I have del by del T of del E by del T, which becomes del square E by del T square. Right. So this is what I have. This is the right hand side of this expression. Right, but on the left hand side I still have this very weird looking expression. Okay, and this weird looking expression can be simplified slightly if you adopt Cartesian coordinate systems. Okay, so by using a vector identity I can actually write down this left hand side as del of del dot E. Okay, this operation makes sense because del dot E is a scalar, but gradient of a scalar will be a vector, so we are all right, minus del square E. Okay. Now is there any way to further simplify this equation? We have assumed that there are no free charges in the region we are considering the wave propagation. So del dot D is equal to rho v and D is equal to epsilon 0 into E. So this implies del dot E is equal to rho v by epsilon 0, but this is actually equal to 0 since rho v is equal to 0. So we have no charges, no free charges in the region where waves are propagating. Therefore, divergence of electric field will be equal to 0. So I can put the divergence of electric field equal to 0 and gradient of 0 is also 0. So this term can be removed. Okay. So I removed that term. So what is that I am left out with is del square E is equal to, after cancelling the negative signs on both left and right hand sides, I get mu 0 epsilon 0 del square E by del T square. It turns out that if you actually calculate the value of mu 0 into epsilon 0, this will be equal to 1 by c square, where c is the velocity of light, speed of light, okay, in free space. So you can write this one as, instead of writing like this, you can write this as 1 by c square del square E by del T square. Okay. This expression which we have just obtained under certain assumptions which are all very reasonable is called the wave equation. Okay. Wave equation for electric field. Okay. So this is the expression that we were looking for. Let's just quickly recap what really happened over here. Okay. We were considering electromagnetic waves that are generated by time varying currents. Okay. Time varying currents will generate time varying H field, okay, which in turn generates time varying E field, which in turn generates H field, and so on, and then you essentially get a wave, and this wave would propagate, okay, and we are looking at the region which is very far away from where the sources are located. It's like these currents which are varying with time, or the source currents, are placed at some far away point in the universe, and wherever I am looking at the propagation of the waves, there are no free charges. I am also assuming that the entire medium is surrounded by or completely filled by linear, isotropic and homogeneous dielectric medium, for which D and E are very easily simply related by a scalar epsilon. For free space, epsilon is equal to epsilon 0. If it is not free space, then it will be slightly different. So we begin with Faraday's law, curl of electric field, okay, and we also wrote down the modified Ampere's law, curl of H is equal to J plus del D by del T. We quickly realized that J was equal to 0 because we are again far away from the region of source currents and charges, and essentially obtained two equations, 1 and 2, which are coupled equations, okay, which couple electric field and magnetic field. Okay. These coupled equations themselves are sufficient to show that waves are generated and propagating. Okay. These are the ones which actually govern the propagation. However, in most cases we are interested in trying to solve these equations. So to solve this equation, we would actually write down them in a slightly different fashion, okay, and that different fashion is obtained by taking the curl of electric field, okay, and then substituting the second equation into the first equation, and then manipulating slightly a bit to arrive at this equation, okay, the one which I have boxed and labeled as 3. In this equation, the right hand side is quite familiar to us, right? I mean, it's just the time variation of electric field. It's just the second order time derivative of electric field, okay. So there is no surprise out there. The left hand side is still not completely familiar to us, right? We have seen probably this in one of the examples where we considered del square A, where A was the magnetic vector potential, but other than that we have not really seen what is this del square E is. This del square E is called as the vector Laplacian, because you remember del square should remind you definitely of Laplacian, but in that case the Laplacian was being applied on a scalar. Del square V is equal to minus rho V by epsilon. This was Poisson's equation, where V was a scalar, del square was the Laplacian operator. But in this case I don't have a scalar, I actually have a vector, okay. Therefore this becomes, or this is what is called as vector Laplacian, okay. Now this is very, very important. This is a vector Laplacian, not the scalar Laplacian. If you expand this vector Laplacian, at least in Cartesian coordinate systems, you will get electric field itself will be x component, right, which could be varying with respect to x, y, z and t, plus the y component of the electric field, which could be function of x, y, z and t, and z component of the electric field, which would again be varying with respect to x, y, z and t. This is the electric field E. So when you apply del square E, what you are actually doing is you are applying del square Ex, x hat, plus y hat del square Ey, plus z hat del square Ez. Okay, where Ex is of course Ex of x, y, z and t. I have just suppressed that x, y, z dependence in this particular expression. Okay, so this is the meaning of vector Laplacian, and such a simple expression exists only because we are working with Cartesian coordinate systems. If it was a different Cartesian coordinate system, then you could not have written down the vector Laplacian like this. You should actually have gone back to this original definition, curl of E is equal to del of del dot E minus del square E, and then in case you were lucky that del dot E was equal to 0, you could remove this from the equation, and then you would have written del square E, the vector Laplacian would actually be equal to minus curl of E. Okay, this is the case for spherical and cylindrical coordinate systems. Thankfully, you don't have to sit and evaluate all these vector Laplacians. Those expressions are available in most textbooks, okay, and in internet, so you can just pick off those values from whenever you are needed. Okay, whenever you require that, you can just pick them off from literature. Okay, and just to emphasize that this is not a simple matter, you have del square of Ex, right, itself giving you del square Ex by del x square plus del square Ey by, del square Ex by del y square plus del square Ex by del z square. So in general, you have three components of electric field, and all these three components of electric field could be functions of x, y, z and t. Okay, what you actually have is a very, very complicated thing in your hand, complicated equation in your hand. So this is what I would wanted to talk to you about the wave equation. Now I would like to consider some special cases, okay, and then try to simplify this wave equation so that we understand how to solve them. Okay, one of the things that we can say is that, well, I know that these equations are linear, okay, and one of the great advantages of a linear system that is described by linear set of equations is that if I know its response to one frequency, right, or if I know the response to a particular frequency, and I can actually build up the response to any other type of excitation, right. This is called Fourier analysis and Fourier synthesis, right. So you take an RC circuit. There are many ways of analyzing the response of an RC circuit to a square input, right. One of the simplest ways to recognize that RC circuit is a linear system, therefore I can take its transfer function. Transfer function is simply the ratio of output Fourier transform to the input Fourier transform, right. But what this Fourier transform is basically how, if you start giving different frequencies, different sinusoidal signals of different frequencies into the RC signal, what would be its response, right. A linear system would always excite itself. I mean, a linear system, when it is excited by a sinusoidal of a signal of frequency omega, will also respond with the same frequency but maybe with different amplitude and phase, and you can actually put together all this amplitude and phase to form the transfer function. The moment you have the transfer function, you can use the transfer function to obtain the response of this linear circuit or linear system to any kind of behavior, different kind of input function that you want. Okay, so therefore recognizing that linear system advantage in our hand over here, we have a linear set of equations. It is possible for me to consider the sinusoidal excitation of the waves. That is, I assume that electromagnetic waves are sinusoidally varying with respect to frequency, and then start putting them together to form the response of them to any other function of time. Okay. So, in view of whatever that I told you just now, we will assume that electric field actually is a function of the variables r, that is perfectly alright, but in terms of its time dependence it would be function of e to the power j omega t. Now there is a reason why I am choosing e power j omega t and not sin omega t. They are actually equivalent to each other, but this kind of expression is quite common when we analyze what is called as phasors for that. In fact, we talked about phasors in Maxwell's equation and we showed how the Maxwell's equation would become, how Maxwell's equation would reduce in phasor form, and we are going to follow that idea over here. Okay. If you at any particular point of time want to know what is a full function, just multiply the phasor with e power j omega t and then take the real part of it, right. So if you want to go from a full function to a phasor, okay, so let us say the full function is basically e of r e power j omega t, that would be the full function, okay, or the real part of it. The phasor form of this will be e of r, okay. You have just dropped e power j omega t and dropped the real part, okay. If I am given a phasor, I need to multiply by e power j omega t and then take the real part of it, okay. So I can then go from phasor to the full time dependent function, okay. If I want to go from time dependent function form of expression to phasor form, I need to drop e power j omega t, okay. So phasors that you might have seen might actually be familiar to you. Those are the complex numbers that are used mostly in analysis of steady state circuits, right. So you must have seen those phasors, and this is essentially the phasors that we are looking at. So we have electric field E of r being a complex vector, okay. Complex vector does not mean that this is some kind of imaginary vectors. What it simply means is that we have chosen to express using complex numbers, but the actual electric field will be real. To obtain that, you need to multiply the resulting phasor by e power j omega t and then take the real part of it, okay. So we will assume that time dependence is in the form of a sinusoidal signal e power j omega t, and then see what happens to our equation, okay. So what would happen to this del E by del t now? This would actually become, because E of r is independent of time, so when you apply del by del t operation onto E of r, nothing would happen, but when you apply del by del t to e power j omega t, it will pull out j omega into e power j omega t, right. So this becomes j omega into e, correct, right. So this is what would happen, and if you differentiate once more, this is just as good as multiplying by j omega twice, that becomes j omega square into e, okay, which is minus omega square e. So I can substitute this into the wave equation so as to write del square e is equal to minus omega square by c square, okay, electric field E. This is for free space, okay, for which mu 0 and epsilon 0 was there. If it is not free space, then you would actually have epsilon r here, c square is still down, right, because epsilon is epsilon 0 into epsilon r, but mu 0 into epsilon 0 is actually 1 by c square. So I get omega square epsilon r by c square. This is for dielectric with epsilon r greater than 1, okay. And you would probably not realize this now, we will discuss this one sometime later. In optics, it turns out that this relative dielectric constant epsilon r is actually related to refractive index, okay, where n is the refractive index, n square. Therefore I can write this as minus omega square n square by c square electric field, but c by n is actually the velocity of wave or light inside a medium of refractive index n. So if I define c by n as v, okay, I can write this thing as minus omega square by v square into e. These are all different forms of the same equation under slightly different forms that we have written, because sometimes using this becomes easy. Okay, so we can say, we consider a medium which has a velocity of propagation which is only 10% than the of the free space, right? In that case, I know what is v. V is 0.1 into c. So I can substitute that and write down this equation appropriately, the numerical values appropriately. Okay. Let's combine left hand right hand side. So move the right hand side to the left hand side. What we get is del square plus omega square by, sorry, I am still in free space, but actually now I am in dielectric, times E is equal to 0. This equation that we have contains no explicit time dependence, right? So it is important to write this as no explicit time dependence. Time dependence is there. Where is the time dependence? Time dependence is sitting in this electric field itself. If I want to obtain what is the actual electric field, I need to multiply this E by e power j omega t and then take the real part. So there is time dependence, and time dependence in this case is very simple. It is just a sinusoidal signal of angular frequency omega. However, because there is no time dependence, explicit time dependence in this equation is known as Helmholtz equation. Okay. This equation is in many cases preferred rather than the original time equation. Okay, at least for analytical cases that is what is typically preferred, but for numerical cases you might want to go back to the original equation itself. Okay, so this is the Helmholtz equation, and we will now look at what possible solutions for this Helmholtz equation can exist.